Artificial intelligence, or AI, is a rapidly evolving field that aims to create machines capable of performing tasks that typically require human intelligence. From self-driving cars to virtual assistants, AI is transforming our world in countless ways. At its core, AI involves developing computer systems that can process information, learn from data, and make decisions or predictions based on that knowledge. Imagine a computer that can understand your speech, recognize objects and images, or even play complex games like chess. These are just a few examples of what AI can achieve. By mimicking human cognitive abilities, AI systems are designed to solve problems, automate processes, and augment our own capabilities. The journey of AI began decades ago, and it has witnessed remarkable advancements in recent years, fueled by the availability of massive data sets and the development of powerful computing resources. As we delve deeper into the realm of AI, we encounter a fascinating subfield known as machine learning, which forms the foundation of many cutting-edge AI applications. Machine learning, a cornerstone of AI, empowers computers to learn from data without explicit programming. Unlike traditional software development, where every rule and instruction must be meticulously coded, machine learning algorithms enable computers to identify patterns, extract insights, and make predictions based on the data they are trained on. Consider a scenario where you want to build a system that can automatically filter spam emails. Instead of manually defining rules for identifying spam, you can employ a machine learning approach. By training a machine learning model on a dataset of labeled emails, spam, and non-spam, the algorithm can learn the underlying characteristics that distinguish spam from legitimate messages. Once trained, the model can then analyze new, unseen emails and accurately classify them as spam or not spam. This ability to generalize from data is a key advantage of machine learning, allowing AI systems to adapt to new situations and improve their performance over time. Within the realm of machine learning, a powerful subset known as deep learning has emerged, pushing the boundaries of AI even further. Deep learning represents a specialized branch of machine learning that draws inspiration from the structure and function of the human brain. Central to deep learning are artificial neural networks, computational models composed of interconnected nodes or neurons organized in layers. These networks are designed to mimic the way our brains process information, enabling them to learn complex patterns and representations from vast amounts of data. Imagine a neural network as a multi-layered web of interconnected nodes, each responsible for processing a small piece of information. As data flows through the network, each neuron performs a simple calculation and passes the result to the next layer. Through a process called training, the connections between these neurons are adjusted, allowing the network to learn and improve its accuracy over time. This layered structure of neural networks is what sets deep learning apart from traditional machine learning methods. By stacking multiple layers of neurons, deep learning models can learn hierarchical representations of data, capturing intricate relationships and nuances that would otherwise be difficult or impossible to model using conventional techniques. A neural network's architecture plays a crucial role in its ability to learn and generalize from data. Each neuron in the network receives input from multiple neurons in the previous layer, performs a weighted sum of these inputs, applies an activation function, and passes the output to the next layer. The weights associated with these connections determine the strength of the influence between neurons. The activation function introduces nonlinearity into the network, allowing it to learn complex patterns that cannot be represented by linear models. Common activation functions include the sigmoid, ReLU, rectified linear unit, and tan, hyperbolic tangent. These functions introduce thresholds and nonlinear transformations that enable the network to model intricate relationships within the data. During training, the network's weights are adjusted through an iterative process called backpropagation, which we'll explore in detail later. The goal of training is to find the optimal set of weights that minimize the difference between the network's predictions and the actual target values. Section 5. The learning process. Training deep learning models. Training a deep learning model involves feeding it with labeled data, where each input sample is paired with its corresponding output or target. The network then processes the input data through its layers, making predictions based on its current weights. The difference between these predictions and the actual target values, known as the loss, is used to adjust the network's weights. This adjustment process is driven by optimization algorithms, such as gradient descent, which aim to minimize the loss function. The algorithm calculates the gradient of the loss function with respect to each weight, which indicates the direction and magnitude of adjustment needed to reduce the error. By iteratively updating the weights based on the calculated gradients, the network gradually learns to make more accurate predictions. The training process is typically divided into epochs, where each epoch involves passing the entire training dataset through the network once. The number of epochs required for training depends on factors such as the complexity of the task, the size of the dataset, and the learning rate of the optimization algorithm. Section 6. Backpropagation, fine-tuning for optimal performance. Backpropagation is a key algorithm used in training deep neural networks. It involves propagating the error signal, which is the difference between the network's predictions and the actual target values, back through the layers of the network. This error signal is used to calculate the gradients of the loss function with respect to each weight, which are then used to update the weights accordingly. Imagine backpropagation as a feedback mechanism that allows the network to learn from its mistakes. By propagating the error signal back through the layers, each neuron receives feedback on how its output contributes to the overall error. This feedback allows the network to adjust its weights in a way that minimizes the error and improves its accuracy. Backpropagation is an iterative process, and the weights are updated after processing a batch of training samples or after each epoch. The learning rate, a hyperparameter that controls the step size of weight updates, plays a crucial role in the effectiveness of backpropagation. A high learning rate may lead to faster convergence, but risks overshooting the optimal weights, while a low learning rate may result in slower convergence, but potentially finding a more accurate solution. Section 7. Deep learning in action, real-world examples. Deep learning has found widespread applications across various industries, revolutionizing fields such as computer vision, natural language processing, speech recognition, and more. In computer vision, deep learning models excel at tasks like image classification, object detection, and image segmentation. For instance, self-driving cars rely heavily on deep learning algorithms to perceive their surroundings, identify objects, and make driving decisions. Natural language processing, another area where deep learning shines, involves enabling computers to understand and process human language. Virtual assistants like Siri and Alexa leverage deep learning models for speech recognition, language understanding, and text generation. Machine translation, sentiment analysis, and chatbot development are other prominent applications of deep learning in natural language processing. Moreover, deep learning is transforming healthcare by enabling more accurate medical diagnoses, personalized treatment plans, and drug discovery. Deep learning models can analyze medical images such as X-rays and MRIs to detect abnormalities and assist doctors in making informed decisions. Section 8. The future of deep learning, a world of possibilities. Deep learning is a rapidly evolving field with immense potential for future advancements. As research and development continue, we can expect to see even more innovative applications of deep learning across various domains. One promising area of research is in the development of more efficient and interpretable deep learning models. Current deep learning models often require massive amounts of data and computational resources for training, which can be a limiting factor for certain applications. Researchers are actively exploring techniques for developing more data-efficient and computationally efficient deep learning algorithms. Another area of focus is on improving the interpretability of deep learning models. Current deep learning models are often referred to as black boxes due to the difficulty in understanding how they arrive at their predictions. Enhancing the interpretability of these models is crucial for building trust and ensuring their safe and ethical deployment in real-world applications. Section 9. Join the AI revolution. Subscribe for more insights. The world of artificial intelligence and deep learning is constantly evolving, with new breakthroughs and applications emerging all the time. If you're eager to stay ahead of the curve and explore the transformative potential of AI, subscribe to our channel for more insightful videos, articles, and tutorials. Our team of experts is dedicated to demystifying complex AI concepts and making them accessible to everyone. Join us on this exciting journey as we delve deeper into the world of deep learning, explore its real-world applications, and unravel the mysteries of this revolutionary technology. Don't miss out on the opportunity to be a part of the AI revolution.